workshop on GPU applications, applications using GPUs, or scientific applications. So let's start from the very beginning here. So during our first, okay, thank you, Daniel, for start recording. During our first session, we introduced what GPUs are, what they offer for computing, for crunching numbers, and the different levels of parallelization, OpenMP, OpenACC, MPI, and CUDA as major alternatives for a parallelization using or not GPUs. And we introduced a little bit how you program GPUs. The focus was more in give you an idea what a GPU more internally is doing, that they work with threads, and those threads execute same operations on different data. So that's how this kind of work has an advantage on GPUs compared with CPUs. And today we will introduce, and also during last session, last week, we show one of the major applications for GPUs, which is deep learning, where you are doing basically neural networks, and the operations for computing those neural networks is basically linear algebra. It's just a bunch of many linear algebra operations, matrix vector multiplications based all the time. So that is something for which GPUs shine, and that's why they are widely used in that area. But we will today explore some other areas where GPUs offer an advantage, and we will see what advantage that is, and in the practicalities on how you can use GPUs in some other context. So another major application of GPUs is molecular dynamics. In particular, what we call classical molecular dynamics or force field molecular dynamics. So the idea of molecular dynamics more in general is to have particles that interact with each other and also with some external forces, some external potentials that could be applied to these particles. In the case of classical molecular dynamics, we assume that those particles have a very defined position, a very defined velocity, which is something that in quantum mechanics we cannot associate a definite value for both quantities at the same time. So we are basically dealing with balls, small particles that collide and interact with each other. And sometimes those particles are just points. They don't have a volume, they don't have a shape or anything like that. And that is one way of simulating atoms. So you put those atoms like point-like particles, and they interact with forces. How you compute those forces, or where you took those forces? Well, there are basically two ways or three ways. You can model those for first principles equations, so equations that come from classical mechanics, and we use the forces from those equations to propagate the atoms in a trajectory, in a simulation. An alternative to that is to use some models. Those models could come from quantum mechanics, or could come from experiments for making experiments with those particles, and we model those and we use those to put in the computer what we would like to simulate. So let's review a little bit, because the focus here is not the technique, the theory of molecular dynamics, more the practicalities of that. So I will go a little bit fast on this, but you can read later on your own pace what is described here. So basically, we are using Newton's laws of motion. That could be put it this way, and the forces could be described as gradient of potential. And we would like to use those forces to go into kinematic equations to propagate particles, to propagate a number of particles following the acceleration that is created by those forces. So one very common algorithm for propagating those particles is the Verlet algorithm. I will not go into the major details of that, but you see the equations that basically is a prescription on how you change the positions of a particle, knowing the velocity and the acceleration at a given time, and also a prescription to changing the velocity of the particle, so the velocity on the next time, using the velocity at the current time and the acceleration at that given time. So with this part of equations, you start moving the particle and changing the values of the position, the velocity, and the acceleration, which comes from the force that the particle is feeling, to propagate the particles on each iteration. So which tiny jump in time, we will recompute all that, and the particle will move a little bit. Well, we will decide that the particle will move a little bit for the next iteration. And we do that for thousands, millions of particles, and with that, we know where those particles will be, and we will start moving those, changing the position, velocities, and so that is the prescription for moving those particles, and Verlet is a very commonly used algorithm for that. We will be doing something very simple. We are focused just again in the practicalities, not in the richness of different potentials that have been created. This is an oversimplification of that. This is one of the simplest potentials. They have some useful purpose of that serves to a certain level, a certain degree of accuracy for a very narrow set of problems. So we have, for example, in this case, we are proposing a potential that just depends on the distance between two particles. It's a pairwise potential. So we have just the distance of the atoms is the only variable that matters here. And this is very crude. And in reality, if you want to get a more accurate description for atoms, they not only rely on pairwise interactions, but also angles and interactions between three particles with angles and dihedrals. So they start considering how this atom also changes the interaction that it will have with another atom at a certain angle. So those potentials could be far more complicated. But right here, we are considering this simple case. Where this case is good enough, or usually for noble gases, is the typical application of that, or when you just want to consider more macroscopic particles and up to a certain extent. But this is the potential. This is called the Lennard-Jones potential. It's been around for many years, and it's like the hello world of molecular dynamics in a way. So you use this sort of potential to introduce many concepts, and after we refine all those things with the ideas of angles and dihedrals to put more to get closer to what we need for a practical application. in this kind of systems. So again, yeah, I told you that this kind of particle, this kind of potential relatively well describe the behavior of atoms in the group 8 of the periodic table. So here you have the values of those sigma and epsilon. So those are the two values that really matters for this potential. Actually, it's just one. If you convert that in dimension, it's just basically one value. But this is the idea. So if you consider the mass, if you put everything in the units, you put the masses for these atoms and the sigma and the epsilon, and that pretty much give you the size of the atom. You mean the size of the atom, it will mean which is the distance where those atoms will be colliding, or they will reach in a stable position. Of course, in fact, they are just points. They don't have any extension on their own. And the way you compute the forces is with the derivatives of those of the potential. And here is just the equation, but we are actually using. And with this and the mass, we know the acceleration. And after, as I told you here, we use that and we inject that acceleration into the Verlet algorithm, and we have thousands, millions of atoms, and we will be moving all those with the code that we have. So there are several codes. I will just describe in one, but I will take the opportunity to show you where the other images for some other codes are. So you go here, yes. So here in shared containers, we have here. Those are all the images that have been optimized by NVIDIA. So we just took those images and convert those from Docker to Singularity. And here I can show you a few that are available. So those are scientific codes for molecular dynamics that can take advantage of GPUs. GROMACS is one of those here, very popular, open source. LAMPS is the code that we will be using today for a quick demonstration, and it has some nuances that I think apply to some other codes, so it's a little bit more complex, so that's why I choose it. NAMD is another package often used to simulate biological molecules. That's another here, and so we have 3 packages here. Those are not the only ones. Those are usually open source or at least academically open packages for molecular dynamics. If you see module available here, I can show you several other packages that could eventually use GPUs. So Amber is another package. I'm not sure if this one is free, maybe not. Especially for biological atoms. So it means proteins. When you mean proteins, you mean thousands, millions of atoms. Usually small atoms, so those are carbon size atoms, so the first lines of the periodic table. Eventually you go up to, if you want to treat hemoglobin or you will have an iron at some point, but for most part they are like atoms. So Amber is here, Gromax is here. So it's see, okay, one old Gromax here with CUDA, a little bit newer here, also with CUDA. But we also had the version that we receive optimized from LAMPS. This version is not optimized, it's not using GPUs, it's just CPU only. NAMD, NAMD, I think the CUDA version should be around, yeah, NAMD is around here, the CUDA version around here. This is another code, again, for biological molecules. And a few other here. So those are packages. So all those packages are classical molecular dynamics. A few are quantum. For example, Gaussian here is this is another package that is actually solving the electronic structure with the basis, so under certain limitations in the theory, it's simulating or is describing the electronic structure, and that electronic structure is the source of the forces that the nucleus, which is where the mass of the atom is concentrated, can generate a trajectory. And a few others here, well, ab init, you can use here for ab initio, or what you call a first principles molecular dynamics. Ab init is around here. Siesta is another code for molecular dynamics with DFT at the DFT level. So density functional materials is an electronic structure description of the atom, and the forces come from that. And VASP. So all those codes are for molecular dynamics. Some of them are first principles. So you use quantum mechanics to describe the atom, the electrons, and the atom. And some are just classical molecular dynamics codes. And for most part, the biggest advantage of using a GPU is when you are in the domain of classical molecular dynamics. So that is why we will be concentrated in one particular code, which is LAMPS. This LAMPS here. Well, not this version, but LAMPS. So let's return here. So what we have. So LAMPS is a code that has been around for quite a while. I think around 20 years, I think, for classical molecular dynamics. Not only particles, not only atoms. So this is a little bit more general. You can describe a variety of simulations, even kind of macroscopic simulations with balls, spheres in 2D, in 3D. It could simulate particles at different levels as far as you can describe the interactions of those particles somehow. So it supports, as I mentioned before, when I described during the previous session about the different levels of polarization or different paradigms of polarization, I mentioned to you OpenMP. So it could use multiple cores on the same computer to accelerate the simulation. You can use MPI, in particular here, one particular implementation MPI, OpenMPI, and CUDA. So that we will be using today, CUDA, to accelerate that. Even better than that, you can mix different of those polarization paradigms, and that's what we will be using. So we will be mixing MPI and CUDA, and we will using 3 GPUs at the same time, simultaneously, to solve a relatively big problem with LAMPS. So that is a very rich package in the possibilities, and also in the configuration that you can do with that. So that you can see that if you click here, it will redirect you to the manual. And the latest version of this code was released a few weeks ago, and it has almost 30,000 pages. So it's a big thing, and it has many options to configure your simulation. Usually the name of the executable for LAMPS is called LMP. Sometimes when you build the code, you can create multiple names, so you can put like suffix to those binaries. So in other clusters, you can see something like LMP underscore MPI, LMP underscore CUDA, because you can compile this code with different settings, different setups for that, and not a single one will satisfy the needs of everybody. So in some circumstances, you end up having multiple versions of this, but all of them usually start with LMP. So you can execute this code. Let me see. Let's start doing this in practice, at least at this level. So I am the head node. I will not execute the code. If you want just to use the CPU only, small load atomistic lamps, you can do this. And you see here, in this case, I create this LMP MPI. So if you want to see the manual, you just type something like this. And you will see like a very short description of the different options. Well, let's see if I can scroll. I will like, okay. I don't need Tmux for this, right? I will scroll. So you see a bunch of different options here. We will be using just a very tiny set of those and here. So, but what it matters to you, especially when you see all the on different clusters, is that you see here lamps, the version that you are using. So sometimes if you receive an input from someone else, pay attention to the version that you have, because people could be using features that only appear on newer versions of this code. And at that moment, when you run the simulation, certain forces are not present, certain flags are not enabled, and it will break the simulation. Or the behavior of some of them, and that is less often now, but it used to be the case, that the behavior of certain flags, certain options, change from one version to another. So you in that case, you need to go back and using an older version to reproduce the simulation. So that is, and this is like a typical example, a minimal example of how configuration execution line works, but we will use a little bit more complex version of that. And those are the options. So in this case, and I did this a few years ago, even before the pandemic, so it's kind of old. When I compiled this version, I use certain compiler. I never enabled OpenMP on that one, but it was using MPI. So that was, I think someone request this code for in engineering. So I compiled that. And this one, again, is not using GPUs, is CPU only, but enabling distributed parallel computing. So it could use multiple computers to do the simulation. And a bunch of extra packages were enabled for them. So this is like a set of user. So those are like Legos that you can enable during compilation things that give you extra features to the code. And so they will tell you exactly what this code was compiled with. So that is the idea of getting first. So this is another way. This is a way of looking at the modules that I have now. So I enable lamps, and those lamps bring me a few other modules. They are dependencies for lamps. So MPI, M50W, HDF, because I enable that to export in the output, the numerical output in a binary format, because they were dealing with millions of particles. So a text file is not a solution for that. But let's move on, because the focus here is GPUs. So I will not be using that. I will be using Singularity. Again, I'm on the login node. I will not be executing anything here. Later, I will be using GPUs. I will submit that. But the way you share containers, and you see lamps, and there are two. No, there are these. I removed it. So that is, in this case, the NVIDIA, what they did was a little bit different. We will see that in a minute. They have user. They have. Like here, no, it's not. Oh, it's lamps. So they have multiple versions of lamps. So NVIDIA compile and optimize lamps for different GPUs. So I will mention that in a minute. So let's go back here. So that's why you access lamps on the GPU. But we will first go into the example that I will be presenting for you today. So, well, before that, lamps in general launches like this. In this case, you will not be using MPI. I'm assuming that the code was not compiled with MPI, so you just put LMP and -IN and the input file. An input file is something that is very commonly used in this sort of codes in chemistry, physics. Is the way we make a setup for a simulation. People in engineering probably is more familiar with user graphic user interface, will create an input and they don't look much into the input. Those inputs could be very, very complex. In chemistry, physics, usually what you do is you write an input file. An input file is a text file, usually, where you describe the geometry, the conditions of the simulation, so both physical and computational variables that are needed for the simulation. So physical, something that is related with the kind of things that we are trying to emulate from nature, to try to get an answer via an acceptably good approximation of what nature will give us the answer for. And computational, which means variables that define parameters that could have an impact in performance, in accuracy, and those, let's say, those are like a different category of things. So here is a mixture of both in this case. So I will be describing a little bit what we have here. What we are creating is a box, like a big box here, where we are putting a bunch of atoms. Those atoms will interact with each other via the Lennard-Jones potential, the potential that I just described here, that I told you works for certain kinds of atoms in the group 8, and this is the potential. So the 612, sometimes the Lennard-Jones 612 is another way to tell it. So here we are describing a little bit some variables, and for most part here is a description of geometry. So where the atoms are, how we will put those atoms. So we are creating like tiny boxes first, with a certain description of the lattice. So the way you arrange the atoms on those tiny boxes, and they will be replicating those in the whole space that we are creating. Some description about, well, but between here and here is some description about the physical properties of the atoms. So in this case, we are dealing with Lennard-Jones potential from a very academic point of view. So the units has no meaning; they are unitless. But the point is, or the mass of those particles is just generic 1, and we are creating all those atoms with random velocities. So you will put those atoms there. They are kind of compact here in this lattice, so they have some possibility to move, but they are not diluted to the point that it's a gas. So that's why it's called like a liquid or a solid that is melting. So the atoms can move. They have a certain medium average distance between collisions, so they behave more like a liquid in that sense. So the other kind of thing, so here physical conditions, those are just the conditions that we need for the potentials. So we'll say, okay, which is the cutoff, or so at which point we are not considering interaction between particles. In principle, the Lennard-Jones potential go to infinite. In practice, you make a cutoff, and we say if the particles is too far, we don't bother computing the force that this far away particle will exert on me. So this is kind of a computational way of making the simulation more amenable, perform better. So after certain point, the force will become 0 from certain distance. Sorry. So, and we will be constraining the simulation under the microcanonical, for the microcanonical ensemble. It means that we have the box, we put the particles in that box. We will not allowing those particles to escape of that box. We will not changing the shape, the volume of that box, and we are not allowing any energy exchange between the particles that are in the box and the outside world. So if one particle is gaining some kinetic energy, is because some other particle or particles are losing the corresponding kinetic energy, such that the energy inside that box is preserved. So those are the physical conditions that in biological simulations. What changes for most part are those. They became far more complex, and they start changing by the different kinds of atoms. So you have hydrogens, they have certain behavior, and carbons will behave differently. And when carbons and hydrogens make bonds, they also change the orbitals, so they means that they will generate angles, and those angles change on the way those atoms interact. So it gets more complexity at that level. That is, again, usually you make a box. That box could be or not periodic, and you put those atoms there, and you decide under which statistical ensemble you would like to make that simulation. Volume will change, or energies can be exchanged if you have a reservoir or something. All that is set up here. So it's in a summary. By the way, I did a small change here. So sorry, this value, I changed from the original example. I'm not dealing with 32,000 atoms. I changed here the size here. So I am dealing actually with 27 million atoms. Much bigger, a much bigger box. I would like to make a very big simulation, because otherwise the GPU will take a significant amount of time. So I make a big box to see a little bit the effect of the simulation. So here is 27 million atoms. So we will have a reduced density. So if we pack the atoms really close to each other, what you have is a solid if the temperature is low enough. So we are just packing, we have a solid. If the temperature is high, you have a solid under pressure, basically. And here are the variables for the forces interacting there, and the fact that we are the MVE, so the microcanonical ensemble, also called MVE, so the fixed number, particles, volume, and energy. So here I am describing again, if you can read here a little bit the description of the different values, or the different variables that we set up here, what they are meaning in the context of this case. So units will be Lennard-Jones. So we assume the Boltzmann constant is 1. We will make everything is just a number. We don't care much. The atom style is just atomic. So they have a full collection of different atom styles. It could be the spheres, and so at that moment each atom will have also a radius. They will have more properties when you make more complex atoms or objects that we will simulate them. The lattice, the region, I told you, big box. We put that box and we put atoms on those lattices. We fill the box with them with random velocities. So that's what I'm doing there. And the coefficients and the kinds of pairwise interactions that we will be using there, and the command for how many iterations we will be running this. So now let's go into the practicalities of that, and we will request 3 GPUs for running this. So I will be leaving here. I am back on the head node, and I will be doing this interactively for this case. So I think I have it. No. Okay, I will copy. Okay. Okay. This is a line, a very generic line for requesting GPUs on Thorny flat. So on this partition, the community GPU inter, I will be using that because I am running with GPUs interactive. Remember, if you try with the standby, you will get an error right away, I think, because there are no GPUs on the standby. So this is a very common mistake. If you don't put anything, it will assume standby, and we don't have any GPU there, so you will get an error. So the partition will be commit GPU inter. I will request 3 GPUs, and most of our machines have 3 GPUs on them. And there is one machine with, but this is when A100s. They have 2 A100 in one machine, and there is one machine that I think it has 8 GPUs. but that is more like an exception rather than norm. On our newest cluster in Dolly Sots, I think the machine, they have 4 GPUs per node, if I'm not wrong. And those are A30s, A1, A40s, so they are from a different generation, very much newer compared with Thorny Lab. And I will be running this for 2 hours, and I will requesting 24 cores. That's it. So really quickly, I got one machine with GPUs, and the first thing that I will do is check what I got via SMI. So I got this machine, and I got 3 GPUs, and those GPUs are Quadro RTX 6000. In the case of these lamps, this is important. Start getting that information. Quadro RTX 6000. If you see, I told you that let's see, load Singularity, and I will get a shell inside the container. Remember, this is important to put --NV to enable the NVIDIA GPU inside the container. Otherwise, you will not see the container shared containers in C lamps patch 3. Okay. So now I have a shell inside the container, and I can execute again the same way. If you forgot to put this, you will not see anything. No GPU will be available inside the container, and either you can rent, or if you run, you will be using only CPUs, not the GPUs. Okay, that is why this is important, because different GPUs will give you what NVIDIA calls CUDA compute capabilities. And here, and here lamps. Okay, here lamp is making a mistake, but this is me using a Mac, and this and inside the Singularity container is making something weird with the terminal. Here they compile lamps with 6 different compute capabilities, also called the ASM number. So you need to pay attention to which compute capability the GPU that you have accepts or is the features that they offer, and you will use in that for running lamps that is optimized for that compute capability. That is, they are ways, but they, for some reason, they never did it here. There are ways to compile multi-capability, let's say, to compile it supporting multiple. They will make the binary bigger, but they never did it for this. Maybe that's better, but I'm not. I don't know exactly why they did it this way. So the first thing is to realize that here, if you see, let me see here, it will explain. Go here. The compute capabilities, what they are, and the different compute capabilities. And we will be focusing in one in particular. So you go to this table here, and you check for the Quadro RTX 6000 that we have. The compute capability is 7.5. We have also the compute capabilities in our documentation for Turing Flat. Another machine, is the P6000. That should be around here. This the older generation that we have, the P6000. The compute capability is 6.1, and newer. I don't know if we have them here. So the A. Maybe they are here. The A100 that we have is 8. And on Dolly sides, we have those newer GPUs. So they are 8 and 8.6. And if you go back here, okay, thank you, Nate. So Nate is confirming that each compute node in Dolly sides is 4 830 or 4 840, and we have 8 A100. So, and you see here all the compute capabilities for Dolly side is pretty much 8 something, while okay, 42 nodes with okay, A100. So it's like 30, 34, 34 compute nodes. I know 37, 34 or 37. Okay, 36, 36. Okay. Okay, so you need to pay attention to this, especially in Thorny, because with the Quadro RTX 6000, we need to go and select SM75, so 7.5. And that is exactly what I'm doing here. So I am exporting this couple of variables here to select the SM75 for lamps. And here I will be picking this. Oh. Started to make mistakes here. Anyway, so I execute this couple of lines here to select lamps for SM75 because I will be running it on RTX 6000, and both for the path and the LD library path. Those two variables you need to set up manually. Again, this is the reason why it is a little bit more complex with lamps, but it's not particularly. It's just that. So the SM number for Quadro RTX 6000 is 7.5, and we select that. So now we have LMP. LMP is there. If you ask for where is LMP, it's right there. And you can run LMP run, LMP whatever, LMP-help, for example, and you will see all the documentation. For, well, the documentation, the summary of commands for lamps here for this code. And what matters here for us is that we are using this version here, which is not that old actually, and that this version have enabled Cocos, which is a library that allow lamps to take advantage of GPUs, where CUDA is enabled. And also OpenMP. So here, OpenMP. So, and they have some other features here for compression or some. Not all the packages are here. If someone needs a specific package, we will have to recompile or make a new version of that, enabling those extra packages. There are many, and some of them are incompatible to each other. So we need to be specific with what we want. And that's it. So there's a long list of variables that we can set up there. And here I have my input file that I described before. It's relatively small. It's one of the benchmark examples in the lamps documentation. So you can go there and get a better understanding of what lamps can do for you. for this kind of simulation is pretty much the standard for macroscopic or microscopic with a very general set of force fields. And the only thing that I changed was using the 30 here and 30 here. This is slightly different, and I am now simulating for 300 iterations. So just to get something that pretty much give me some time for demonstration. So now it's time for me to submit this. So we have here this, we have here. Okay, a couple of variables is just because I will be changing this and making 3 simulations to show you, the purpose here is to show you how to use GPUs and why using GPUs give you an advantage. So for that, I need to compare what if I use 3 GPUs, why if I use just 1 GPU, and why if I just run with just the CPU. So that give you a very striking idea of why these GPUs are so important in molecular dynamics. So I will be setting those couple of variables to run the simulation. And here is the line for running this, for running labs. And I will be explaining all this in detail. Wait. It actually took the line. That is a mess. Well, I will describe it here and I will paste it in. So this is the line. It's not well visible when I paste it on the terminal. So remember, I will be using LAMPS with MPI. So that's why I have this first part here. So I will be using MPI, and I will creating the same number of MPI processes as the number of GPUs. So each GPU will be associated to one MPI process. So this is the first part. So LAMPS will be using MPI. MPI will allow me, in principle, to use multiple machines. That's not what we are doing here. We are running on the same machine. But the library for passing messages is there. Now, this is the code that we will be using. The binary is called LMP. This is LAMPS. So the first section here, from here to here, is saying that we will be using Cocos, which is the library, enabling GPUs, so enabling on the GPUs and the number of GPUs that we will be using, 3 that we set up here. So we set this variable here, so we will be using 3 GPUs. So here, this suffix is because the style of the particles that we define here in the input is right here, the style, the atom style here. If you see the documentation, they have variants of those styles, and some of those variants, if they have the suffix KK, they can be accelerated with Cocos, so they can be accelerated with GPU. So that is what I am doing here. So the style will have the suffix KK, and this is a configuration for the GPU here. This is a little bit beyond what we can present here, but those are how we enable the GPUs and how we will distributing the work for the GPUs, what they will be doing. And a few variables for the boxes here, the size of the boxes that we have here in the input file. So how big that box will be here by default is 1, but you can change that out of the input file during the command line, and that configuration, the command line will take preference on top of whatever is inside the input file. So that is wait a minute, is here. And the input file. And the input file, we say, is this input file. So this is the submission line to the execution line for lamps using the GPUs. So we will clean this. Not even this works. Okay. And it will start launching that. You will see from if I can stop. Well, it is running, but it runs for a few seconds. So here you will see that I'm enabling 3 GPUs, and I am using 1 MP thread per MPI task here. And I have a total of 27 million atoms. So that's the number of particles that we put in that box, all of them with different velocities, with a certain seed. Well, it finished. It finished. It took 39 seconds to run that for 300 iterations. Yes, 300 iterations. So 300 iterations, all those. And you get some statistics if you want. That's something that we are not doing here, but in the case of a workshop for lamps, for molecular dynamics, we usually take those and we make plots of the energies or the pressure, different physical values that we can capture on the simulation, or eventually the trajectory of those particles that we can put in a code, in a program to visualize, to make an animation or something. But right here, what we are interested in is how good we can do a simulation with 27 million particles. And the answer is 40 seconds, 3 GPUs. Okay, so now what we will be doing is just demonstrate pretty much the same thing. Let's see. I would have to do it here. So instead of this, I will be using 1 GPU, and I will be and I will be running exactly the same. So now this time 1 GPU, 1 MPI process and 1 GPU, and you will see the difference. I made a very extreme case, 27 million atoms. So that means that I will be relatively close to perfect scaling in that. When you reduce the size of the system, the system they have, like, let's say a few 100,000, using more MPI processes or using more GPUs will not necessarily cut the simulation time by the number of GPUs. There is always an overhead in communication, in extra memory that needs to be used because there are portions of information that need to be shared between the different MPI processes, the different entities. So there is overhead in memory, there is an overhead in communication, and that, especially the communication, will reduce the ability to cut the simulation time, just divided by the number of CPUs or the MPI processor or the number of GPUs. So in this case, it will take, I think it's 2 minutes, but in the meantime, I will describe a little bit. So I will be running this. Okay, 27 million atoms. And this is when I ran with 3 GPUs. When I did this, when I prepared this, it took that. When I run it with just 1 GPU, it will It took 2 minutes, so it took exactly the same. It took 2 minutes. So, well, pretty much it's perfect scaling. For 40 seconds, 3 GPUs, well, one GPU is taking 3 times more. But that is a very idealistic case, and for many reasons, because we are using Lennard-Jones, because we have 27 million atoms, because the box is a perfect cube. For many reasons, and those things are very idealistic. So now, what about if we are not using? Oh, let me see if we can do something here. Export OpenMP numbers. I never tested. Oh, export OpenMP. No. It will make a difference. No. Okay. No, I never test that. So what I have here is, what about if I just run 3 MPI processes, but not GPUs? In that case, I will be cutting all the Cocos. I will not be making any mention to this. I will not using Cocos here. And so not this, not this, not this. But I still keeping the same size of the box, three CPUs. It will be taking 3 CPUs here. And so the simulation will be like this. So we have, oh yeah, now we got it. So now I am not enabling GPUs, but now I am using two OpenMP threads per MPI process. So I think I am using actually 6 GPUs. So I probably will get a better figure compared what I put here, which is good because otherwise you will have to wait, and you have to believe me, because we will not be waiting 24 minutes to get this done. So when I did it using just one MPI process, one MPI OpenMP thread, and 3 MPI processes, it took me 24 minutes to simulate this, to simulate exactly the same. So you see the advantage very clearly, the advantage. You move from something that is taking basically half an hour to something that is taking less than a minute, just by using 3 GPUs. So they really, really help simulations, and that is why they are so widely used. So yes. So let's see. Wait. I okay. So Patrick, who prepared this section, he is feeling bad. He is ill. So let's see what if I can try to reproduce what he prepared for us with other applications. Basically, what I would like him to mention are other packages. And by the way, I can mention a few other packages here that can use GPUs. One is, for example, MATLAB. And here, if you select here, there are some other packages that can take advantage of GPUs here. Apart from deep learning, we saw that previous session. So deep learning are MXNet, Paddle, PyTorch, and TensorFlow, the 2 versions of TensorFlow. Those are deep learning stuff. Molecular dynamics, GROMACS, LAMMPS, NumD. that we have here optimized by NVIDIA, so those here. Some other packages, apart from those, are Rapids, which is a package for simulations, so accelerated with GPUs. For more general simulations. So if you see, we see Rapids, I think it's NVIDIA Rapid. The word is very interesting. I've never used it. But here they will describe what they are. So it's Python all again. So you can use Python, and they have like things that you can do with that. Another thing that we can accelerate with GPUs is a Spark, and the Spark is for big data, big data analytics. So those RDDs can be set up for living on a GPU, and you can process those data frames in the Spark using GPUs. This is relatively new. It appears a few years ago. And Monai, which is another, let me see if I'm missing something. So it's Rapids here, and Monai, which is another package that and Julia is another language that is very efficient. It's far more efficient than Python. It's kind of niche, so not many people use it, especially people who need something to fast development and also fast execution. Julia is very good at that, and NVIDIA now incorporates some modules where they can take acceleration with GPUs. And Monai, I really, honestly, don't remember. Monai. Okay, this is something for healthcare that I never actually presented, but yes. So this is basically for processing CT scans or that sort of things. So they have like a framework that is guided to health science and machine learning. So let me see what we like what we have from Patrick. So okay, computational fluid dynamics. Okay, we have basically nothing. Okay, so one thing that we can use here that I just mentioned, because there is nothing there, is computational fluid dynamics, ANSYS, both ANSYS and MATLAB. Both are big packages, usually with a graphic user interface that can use GPUs. Unfortunately, we don't have anything there to show you there, so we will be pretty much closing this workshop earlier today. So that is what I would like to present, less than I would like to present, on the different ways of using GPUs. And again, the motivation for this is we have a new cluster and that will be in production in a few weeks, 3 weeks, 2 weeks, I don't know, in a few weeks, 1 month maybe, will be available for you. You can request accounts on this cluster, and this cluster has more than 150 GPUs, and you can use those, for example, for deep learning, for training your deep learning models, either from scratch, or you take another deep learning model and you just repurpose it for your research, which is what most people do. You take something big and they eliminate the final layers, and they train the machine for your purposes, or for example, modeling molecular dynamics, for which GPUs are extremely good. You see, this is still running here. You see It's still taking, it will take probably less than 24 minutes, but there's still something like around 20 minutes or something, 15 minutes at least. So it's considerably slow compared with using GPUs. And there are some other packages, and we will eventually start installing more packages on Dolly salts, taking advantage of the GPUs. Some of the new versions of GPUs are so good, and they have enough amount of memory that ab initio molecular dynamics can now efficiently take some advantage of that. So the big limitation for ab init at that time, I'm talking with when I did my PhD, so like more than 10 years ago. The big problem with DFT at the DFT level and using GPUs is because the memory on those GPUs was not enough for making the simulation efficient. Because we have to put all the parameters for the fast Fourier transform and do the fast Fourier transform inside the GPU. So the codes were not really taking advantage of that. But that have changed. You see machines today, they have 24 gigabytes of GPU RAM. Some machines, one of the A100s, they have 40 or even 80 gigabytes of RAM. So at this point, and the number of CUDA cores start making a case for moving some of those packages to take advantage of GPUs, and some of them start being optimized for GPU. And NVIDIA is also taking collaborating with the developers of those codes to enabling GPU. So VAS, for example, NVIDIA people took the code and did the changes for accelerating that with GPUs. So you will see more and more of those packages enabled on Dolly salts for GPUs, and also for big data, for data analytics on, for example, Spark, taking advantage of GPUs. With this, we will be closing this workshop. Tomorrow will be the final session for the introduction to HPC, and on Thursday will be the final session for interactive applications with Python. So with this, thank you very much, all of you. Sorry for finishing earlier for this workshop. And see you tomorrow, or thank you very much for your assistance to today. Then Daniel, if you can, thank you. You now read my mind. See, Daniel just post the link for the form. So if you are just attending this workshop, please do not forget, take a few minutes to fill the form. That helps us to identify what you want, and we present those workshops not only because they serve your purpose, and also because the funding agencies ask us to make this kind of training possible. So this is important for us to get sustainability with the clusters in the future. Those machines are very, very expensive. They are, and we need, and they deprecate very fast, especially machines with GPUs. Those machines, after 1 year, 2 years, they start getting old, and they are very, very expensive. So funding for that needs to be flowing with a certain regularity. And for that, we offer these kind of workshops, and also for you to take advantage of these GPUs for your research. You produce more papers. Those more papers bring recognition to the institution, and that is what these universities strive for: recognition and funding. So please fill the forms. That will help us a lot. Nate is mentioning, and he's right, we got the machines delivered. The machines are in the room. They are very, very new in terms of the GPUs that they have. You see they are for GPUs, they are very, very powerful. Not many machines And so now we start having a balance. We have a cluster that is CPU intensive, and we have a cluster that is GPU intensive. So that serves two different worlds, two different environments, two different user cases, and that's why we offer this version for you this time. So thank you very much, and see you in a new workshop.